everyone. So this little lecture is going to be about what we call the Copernican Revolution. So this is kind of an introduction to what we're going to be talking about with gravitation, just a little bit of history behind how we view our solar system today. So back in the day, and this was a long time ago, like we're talking 16th century. This was before like 1550, I want to say, around there. Everyone believed that the Earth was the center of the universe. And we call this the geocentric model of the universe because, again, geo, that's Earth, and geocentric means that the Earth is the center. And everyone believed this. So obviously, we're very full of ourselves. We think that we are just amazing and the center of the universe. So obviously, everything revolves around the Earth, right? So this is what everyone believed back in the day, in the 16th century. Now, along comes Copernicus, and this is in about 1543 when he kind of came up with this theory for a heliocentric model of the solar system. Helio meaning sun. So what this means is that the sun is actually the center of the solar system and everything revolves around the sun. And this was a very crazy idea to everyone because literally everyone else believed that the Earth was the center of the solar system, the universe. So because this was such a different idea, it was crazy to people, So the reason that he believed that the sun was the center of the solar system is because he was observing that planets seem to loop backwards as they travel on what he called their crystal spheres. And the reason that they loop backwards like this is because of a parallax view, and we'll talk about that in a second. But he was like, okay, there's like two explanations for this. Either number one, our Earth is the center of our, universe, and this planet is going to do this weird loop-the-loop thing to match that loop-the-loop that I see in the sky. Or our Earth is not the center of the solar system, and actually the sun is the center of the solar system. And so when Earth overtakes this other planet right here, it seems to move backwards. And so this obviously is what we actually know is happening. But this is an explanation for if the Earth was really the center of the universe. But this is kind of crazy right here, obviously. So this is how he came up with this idea of the sun being the center of the solar system, or the heliocentric theory. So, like I said, the actual reason for the looping appearance of planets is because of what we call a parallax view. And parallax just means that the position or direction of an object differs when viewed from different directions. So we can see that as Earth overtakes Mars, it's kind of going to look like Mars loops backwards and then goes forward again. Because again, Earth is closer to the sun, it's going to be moving faster, so therefore it's going to overtake Mars like that. So Earth overtakes Mars, making Mars appears to go backwards relative to the background stars. Now, so Copernicus comes up with this crazy idea, and everyone's like, "You're crazy, man." And, he's not getting a lot of people backing him up. But then this guy comes around, and his name is Tycho Brahe. Tycho Brahe is credited with a lot of different astronomical discoveries and, inventions and just tools that we can use to observe the universe and things like that. But what he did is he actually measured precise positions of planets and stars in the sky, and he actually was able to settle this issue of heliocentric versus geocentric models. So he was actually able to prove with his instruments, with his measurements, he was able to prove the heliocentric theory that was put forth by Copernicus. And this was between the years of 1575 to 1596. Now, in 1609, so not much after this, Johannes Kepler came along, and we're actually going to be talking a lot more about Kepler's laws in our next couple lectures, so we'll go deeper into these laws. But he came up with 3 laws of planetary motion. And his 3 laws were, number 1, planets orbit paths that are elliptical in shape. And like I said, I will talk more about that in a bit when we talk about Kepler's laws in kind of the second part of this unit. But elliptical means it's kind of oval, like you can see on the screen here. So obviously planets, we model a lot of the time, we model them as a circle, their orbits, but their orbits are actually elliptical in shape. His second law was that planets sweep out equal areas in equal times, meaning if we look at this picture right here, we can see that the Earth is sweeping out this distance right here in this area when we are looking at the distance from the Earth to the Sun and the distance that the Earth travels right here. Now, this is a month's time, and this also, when the Earth is closer to the Sun, is also a month's time. If we measured these areas here, they would be the same, but the size of the pizza slice that we call it, that I like to call it, we either have a short, fat pizza slice or a long, skinny pizza slice. That size and shape really is going to depend on where the Earth is oriented in that elliptical orbit. But the area, wherever it is, if we're measuring the same amount of time, is always going to be the same. And then last but not least, Johannes Kepler's third law of planetary motion is that we have what we call a Kepler's constant. And this is a constant for objects that are orbiting the same body. So meaning each planet that's orbiting the sun will have the same Kepler's constant. Each moon that's orbiting Jupiter will have the same Kepler's constant. Any satellite that orbits the Earth, so we're talking about like the moon or the International Space Station or any other satellite that orbits the Earth, they will all have the same Kepler constant as well. And don't worry about this too much, this t squared over r cubed. We'll talk more about that when we actually look at Newton's universal law of gravitation, the velocity of a satellite, and all of that stuff. Will actually derive this term right here for Kepler's constant, and then we will use that, and I'll show you how to use it for different planets and things like that. So those are Kepler's 3 laws. So like I said, this is law number 3, and this is that each thing that's orbiting the same body has the same Kepler's constant. So in this case, we have 2 moons that are orbiting the same body and also a satellite that's orbiting that same body. Those things will have the same Kepler's constant because of Kepler's third law, which is named the harmonic law. And like I said, we will go deeper into this when we actually go deeper into Kepler's laws. Last but not least, I wanted to talk about Galileo. So in 1609, this was like about December 1609 into January of 1610, Galileo was able to show that moons orbit Jupiter. And this was huge because before this, telescopes were not really very powerful. So he was able to make this telescope super powerful so that he can actually see the moons orbiting Jupiter. And because of this, the 4 largest moons that orbit Jupiter are actually called the Galilean Satellites. So they're like, named after Galileo, kind of. So this was a super radical discovery because, like we said, it contradicted this popular belief that all heavenly bodies orbited the Earth. So now we have all these, scientists and astronomers and everything that are coming out saying that, oh no, actually not everything orbits the Earth. So everything that we've believed up until this point, is not entirely true. So this was huge. And it was really when people started changing their thinking, which again is just a very, very big part of history. Now, this also proved that the moons orbiting Jupiter obeyed Kepler's laws, which was really big as well because Galileo was able to prove Kepler's laws, which helped Kepler out a lot because he was publishing these things and obviously having a hard time to get people believing him. But because Galileo is now kind of backing him up, then he gets some credibility as well. So that's pretty cool too. So that's kind of a brief history behind our planetary motion and beliefs and how those beliefs changed. Now, in the next couple lectures, we're going to learn more about, Newton's universal law of gravitation, and we're going to learn about Kepler's laws so that we can actually put some math to these different motions of the planets and things like that.